Hello, again, good morning, and welcome to Breakfast with Arab. Great to see you, very noisy bunch this morning. I guess you're all happy and well from the summer we had a few days ago, which is now over. My name is Farah, and I am the Marketing and Communications Leader for Building Engineering London. And so to our speaker this morning, Stuart was born in Southend in Essex, and his father worked at the Ford Motor Company in Dagenham. Stuart did not really intend to go to university, and he left school at 16 and attended Southend College of Technology to study a diploma in mechanical engineering. However, Stuart was messing around so much with his friends, he realised he wasn't going to pass his diploma and thought he would go and get a job instead. He duly went off to the local job centre and found a role for a civil engineering technician at the Borough Council. Being a typical Essex boy, he drove a Ford Escort Mark I. His second car was a Morris Marina, which was white and painted with a red Go Faster stripe. Stuart and his friends, who also owned a blue and a red Morris Marina, were quite the lads driving around Southend. Whilst working, Stuart started day release course studying for an ONC in civil engineering. It was a combination of study and work that really inspired Stuart. City University in London ran a sandwich course to study for a civil engineering degree. And whilst he was studying, he also went to work in Copenhagen for a contractor, and he also worked for Atkins. Completing his degree in 1990, Stuart had a place on site at Drax Power Station where he worked for National Power. He also decided he wanted to study for a master's, and he was not sure whether he would study for a master's in steel or structure. Serendipity once again played her sweet magic, and he rang up Imperial College, and he happened to be put through to the concrete structures department, and that's how he started his career as a structural engineer. Still during the recession, Stuart went to work for Robert Bername, who had a niche practice preparing bridge designs for contractors, and he really enjoyed this role. He did find, however, that bridge engineering was rather analytical and wanted to broaden his experience. He went off for some interviews, including here at Arup, and joined the firm in 1995. His career with Arup can be summed up in 2 decades, the first 10 working primarily in London and the second 10 working internationally. His portfolio of projects include Stratford and Ebbsfleet Station at CTRL, Blackfriars London Underground Station, 88 Wood Street with Richard Rogers, the support structures for Millennium Wheel and Tate Modern. Internationally, Stuart has worked on TVCC Beijing, Beirut Terraces Lebanon, Miami Art Museum Florida, M+ Hong Kong, BBVA in Madrid, and Reforma 509 in Mexico City. Closer to home at the moment, Stuart's working on the Lord's Warner stand. So, without further ado, I'm really happy to introduce the wonderfully enigmatic Stuart Smith, who will share his thoughts on living in a material world. Thank you, Stuart.
Thank you, Farah. I'm not really sure now why I shared all of that with Farah, let alone gave her a photograph of a car that I self-customised. But there you go, it was Southend. My talk today is about materials and the material cycle from beginning all the way through to the end. And I was first inspired to look more closely at this topic by the photographs of a Canadian photographer, Ed Patinsky. His photographs show great landscapes that have been altered by the things that we've done and the things that we do. This image shows oil derricks in North America, stretching out for as far as you can see. And this image, coal mining in China, huge great piles of coal, again stretching as far as you can see into the landscape. And then looking at some of the materials that we see in the built environment, marble. The biggest producer of marble is Italy, and most of it comes from a single source Carrara. But that's a very beautiful region of the world, Tuscany, and the mining has damaged the landscape, and the conditions in which the quarry workers work are quite difficult. The dust causes lung infections, and the working conditions scrabbling around on the marble are quite treacherous. And then copper, great big copper mines. The concentration of ore in copper for 150 years ago was about 7%. That's now declined to 0.6%. So we have to mine increasing amounts to get the same amount of material. And at the same time, our consumption goes up. And this photograph in particular really captured my attention, the stark contrast between the red and the black. And I wanted to know more about nickel and what that meant to us and what we used it for. Nickel is a component of stainless steel, and we probably all take stainless steel pretty much for granted, and we've probably all got a bit of it in our mobile phones. So looking more closely at nickel, I found a study in The New Scientist from 2007 that talked about the finite limits to our materials. In 2007, they looked at nickel and told us that nickel would expire in 57 years. And chromium, another key ingredient of stainless steel, would expire in 40 years. Now that study led to a lot of research and thinking around the topic of materials and their finite limits, and a number of these statistics have been challenged. But what everybody agrees about is that our materials are a finite resource. They won't last forever. And perhaps one of the more interesting statistics that I picked from the New Scientist study was on silver. We've been depleting our silver stocks for around 60 years, and at current rates of consumption and supply, we only have another 9 years of silver left. And silver is quite a key component in mobile phones as well. So whilst silver isn't mined directly, it's a byproduct of other mining. 1 tonne of mined material will yield 3 grams of silver, whereas 1 tonne of mobile phones will yield 3,000 grams of silver. 1,000 times more silver in our mobile phones than in a tonne of mined material. And this is our consumption of nickel. Over the last decades, it's increased exponentially. And that's a similar pattern for all of our materials. But perhaps as well as having finite supply, there are also geopolitical issues. So the location of our resources is not evenly distributed. In America, they were mining rare earth elements up until about the 90s. They stopped because production in China was so high. They'd flooded the market and the price had gone down. So they stopped their production and relied instead on China to supply these materials that we rely on for batteries, mobile phones, computers and so on, become quite crucial to our daily lives. More recently, China stopped supplying these materials in such quantities and the prices went up. And you can just see in the bottom corner, America has just started to mine these materials again so that they have security of supply. So there are geopolitical issues around the supply of our materials. This wonderful image from Montana, it's an image that we know well from the film A River Runs Through It by Robert Redford. It's a very beautiful natural environment in North America. But over-extraction of materials has made a big difference to this environment. In the book Collapse by Jared Diamond, he covers this very well. It's a book all about collapse of societies, often due to over-extraction of materials and lack of care of the environment. So in Montana, mining for many decades has led to over-extraction, polluted water sources, then logging of the hillsides has damaged the landscape, allowed rainwater to leach out nutrients in the soil, and has caused decades of damage to Montana. But one of the main impacts of that is that the local population can no longer make a living there, and they've started to leave. So there are societal impacts to our material extraction as well. And then whilst I didn't, at the beginning of researching this topic, I didn't want to dwell on embodied energy and carbon, but I found it was so significant that it was important to talk about. So as an industry, the building industry has spent a long time over recent decades thinking about our buildings in use and the amount of carbon they emit. So we know that by 2050 we have to limit carbon emissions by about half of what they are now. And we've studied that quite extensively when it comes to building energy use. So we understand we need to insulate our buildings, use lower energy systems, and find renewable sources. But our buildings emit approximately 9 gigatons of carbon into the atmosphere each year, whereas our materials are responsible for 3 gigatons of carbon emissions. That's construction materials, not all materials, construction materials. So to me, that's quite a significant amount of carbon that we need to reduce by 2050 if we're to meet climate change targets. So embodied energy in materials is quite a significant issue for the construction industry. To try to give you an idea of what a gigaton is, I wanted to try and do that by weight. And I started off with some quite small things like elephants, but there were so many I couldn't reach any kind of number that would mean anything to you. So I went for the biggest thing I could find information about, and there happens to be a very good fact sheet for the Empire State Building online. So the Empire State Building, I now know, weighs 330,000 tonnes. So 3 of those is 1 million tonnes, 3,000 of them is a gigaton, and 9,000 of them is 3 gigatons. So by weight, we're emitting 9,000 Empire State Buildings in carbon into the atmosphere through our materials. And to give you an idea of something else that we consider important to reduce carbon emissions, air travel is responsible for around 2 gigatons of carbon per year. So that puts materials into perspective. And most of our carbon emissions, of course, come from steel and concrete. So I'm going to talk a little bit about steel and concrete and what we could do about those. So steel, we make 1.6 billion tonnes of steel per year. About half of that is made in China, and about half of the steel we make we use in construction. What I found surprising is that about half of the steel we use in construction is actually used in reinforcement. So reinforcing bars for concrete. So that's 400 million tonnes of steel used in rebar. And actually our design and production of rebar hasn't changed very much in decades. So maybe if we could improve the way we use reinforcement, we could make some quite big changes. Microalloying was really understood in the 70s, as recently as the 70s, and by adding small elements of niobium and vanadium to steel, we can increase the strengths by about 20%, therefore using less steel. And we could do this both for structural steel and for rebar. So now talk about steel process. There are 2 primary processes for making steel. One is a blast oxygen furnace, and the other is an electric arc furnace. Blast oxygen furnaces need to run pretty much continuously and use fossil fuels. About 75% of the world's steel is made using blast oxygen furnaces and 25% electric arc. But electric arc furnaces can use recycled steel. They can also use renewable energy sources if it's available. And because they're more nimble in terms of being able to start and stop, they could also use off-peak electricity. However, most of the steel around the world is made with blast oxygen furnaces, and it's interesting to look at the bids for Port Talbot, and Liberty House in particular are talking about saving the electric arc furnaces and phasing out the blast oxygen furnaces. This really would be the future of our steel industry. But at the moment in this country, we're only making 14% of our steel with electric arc furnaces. But the steel that is born in the USA is 61% electric arc furnace. So they're ahead of us in what they're doing. And now when we talk about concrete, we really only talk about cement. About 97% of the carbon emissions in concrete are from cement. So the theoretical minimum amount of energy you need to make cement is 2 gigajoules per tonne. Best practice is about 3 gigajoules per tonne. However, the world average is 5 gigajoules per tonne. And that's predominantly because the processes in China use a wet process which requires more energy, therefore bringing up the amount of energy globally that we use to produce cement. So what can we do? We've got some quite big impacts from materials and the materials we use in construction. What can we do better? This is a project I came across recently. We're increasingly using more sophisticated computer analysis to better optimise our structures. This is an example from the Riyadh Metro project we're working on now. one of our engineers took a simple piece of computer code and looped the analysis to find the optimum solution. So on this project, we saved 5% of the materials by using more sophisticated analysis. And that, of course, equated to money. That was $2.6 million. At a much bigger scale, this is Sky City in China. And ever since I saw it, I've been fascinated by it. It would be the tallest building in the world, 828 metres, and their plan is to build this within 12 months. And they've already trialled this. They've built a 40-storey building in 19 days, so they can do it. It's true. And they've built, so they use an off-site process, so it's a completely prefab, so minimising waste from construction and building very rapidly. But also our team are optimising this structure, and when you get up to this scale of structure, then you can make bigger savings, 10 to 20% of the material can be saved using similar analysis. Then we could look at reuse of our projects or reuse of our building stock. So this building is in Paris. It's by an architect called Lacaton and Vassal, who are very good at dealing with reuse of buildings. Somebody had already had a go at refurbishing this building, and it had been fairly disastrous, and it was known locally as Alcatraz. Not a complimentary title. But the architect came along and took the front of the building off and added an extra bay to create these rather beautiful winter gardens. And that's now a very successful building. Now, I guess we have other examples in buildings like Trellick Tower and Park Hill in Sheffield in the UK. And then there are lower energy alternatives to steel and concrete. This is Believe in Better at Sky, a project that uses a timber frame, so much lower embodied energy than steel and concrete, and was built very quickly. This was 12 months from start of design to completion of the building. And then this project is a project in Austria called the Life Cycle Tower, where we've replaced timber for concrete. So you see the composite floor panels here. We use a concrete core, but a load-bearing timber facade. So we've started to mix and match materials into the design process. And then I recently completed the concept design for a project in Vancouver. This is the Vancouver Art Gallery. In British Columbia, they have a wood-first policy. So before you design in steel and concrete, you have to consider your building in timber. More recently, we've had Hackney Council flirting with a wood-first policy, but that has provoked a series of CLT cross-laminated timber projects in East London. But there are also finite limits to what we could do with timber, and at the moment we could do a lot more in timber, but we certainly in the long term can't solve all of our problems by building everything in timber. There are issues of demand on land, and land we use for agriculture, for feeding a growing population, and for biofuels for other purposes. So there's also a limit, which we're a long way away from, on what we can do with timber. And at the same time, across all of our construction materials, our consumption is increasing. And then there's the issue of waste from the construction industry. In the UK, we generate 163 million tonnes of waste. The construction industry is responsible for about half of that, 85 million tonnes of waste in the UK. That's the equivalent of taking 255 Empire State Buildings and discarding them every year. So there's quite a significant amount of material that we simply discard and throw away. In London, that's 20 million tonnes of waste and 9.5 million tonnes from the construction industry. That led to some problems with landfill. Although the construction industry is improving, demolition now, we divert 80 to 90% of our material away from landfill. But the material is generally downgraded. It's used as road fill or landscaping. So whilst we're not adding to the landfill problem, we're still downgrading our materials. So I'd like to propose that we see our cities as material banks, a place where we could store our materials and come back to them later for reuse. So if we could take our materials and upcycle them, whenever we come to a project in London, we always find there's something there already, And generally we regard that as an obstruction, as a waste product. But if we could find ways to look at it as a material asset, as something we could upcycle, that would be a benefit to all of us. And more recently, we've heard increasingly talk about circular economy, which came from a couple of British economists who talked about the idea of optimising the system rather than optimising the elements. So we can see we can optimise the elements, but we're still using a lot of materials. The circular economy suggests that we could take our materials and put them into a cycle where we reuse and keep them in circulation. The project here is one of the first projects built in accordance with the principles of the circular economy. It's Brummen Town Hall in Holland. And all of the products that make up this building are supplied by suppliers and owned by suppliers, and at the end they take them back again. So you pay for performance rather than products and materials. And there's a plan for what to do with them at the end. And we're starting to see the circular economy applied to the manufacturing sector, which is now coming into the built environment. So this is a very good example from Philips, where you pay per lux. So you pay for the lux levels and the lighting service in your building, and Philips supply the light fittings and the bulbs, and they maintain them, change the bulbs, take the fittings away when they're expired and replace them with new ones, and they take on the responsibility for recycling them. Our facades team are looking at a similar model for performance-based facades. So you would pay for a certain performance, a facade manufacturer would install the facade, but it also implies they would monitor that performance over time. So as new materials become available, they could come and change those materials for better materials and better performance in terms of thermal performance. And when components within that system start to wear out, they could be individually replaced rather than the whole system being scrapped. So you never own your facade, you just pay for the performance. It implies that we need to come up with a way of building that has lots of pieces that we can take apart at the end. Recently on Leadenhall, 85% of Leadenhall was made using off-site construction. Now, it wouldn't be easy to take Leadenhall apart, but the starting point is that we are able to put it together with a series of components and pieces, and therefore should be able to plan to take it apart. And to do that, we need really good information. If we're going to have a materials bank in our buildings, we need really good information about the materials we put into our buildings. So the idea of using building information modelling to store information about our materials so that when we come to disassemble and reuse, we know exactly what we've got, we know what we've put into it, and we know what we're taking out, and we have a plan for what to do with that. And there are various ways of looking at materials and their circulation. Cradle-to-cradle thinking provided a framework for that. But these are frameworks, whereas I think the circular economy also provides a business model. It deals with one of the important aspects of sustainability, and that's the economy part of it. And another example of this, the living building challenge, where buildings would be more positive to the environment than negative. This is one of the main buildings built under this challenge. It's in Seattle, it's the Bullitt Center. And at the moment, it's attracting a lot of people to go and visit it with an environmental interest in a similar way to Bed Z and how that raised the profile of environmental design. Except that this has a huge solar array on the roof to make it work as a standalone building, and it uses a timber frame. So whilst this works for individual buildings, it's not necessarily a model for a whole construction industry. And when it comes to embodied energy in materials, our standards are playing catch up. So 5 years ago, BREEAM and LEED had very little in them on materials. And in fact, at the Olympic Park, both the Velodrome and the Aquatic Centre achieved BREEAM Excellent, despite quite different approaches to their material use. So maybe we should see our buildings as a series of layers. And Stuart Brand first proposed that idea. A series of layers that we can look at in different ways and have different timelines and different design lives for each of the layers, so that whilst we can quite easily see how to deal with the circular economy and how we might recycle our materials in terms of a fit out, it's going to take us much longer to figure that out for a structure. But maybe if we take a temporal approach to our design process and each of the parts of a building, we could start to solve this problem. And as a structural engineer, we're quite often given design lives of 50 years for a building. Yet we know that the structures that we design could be altered quite significantly within 20 years of building. Or alternatively, they could be kept for much longer, centuries even. So thinking about this in a longer term, the longevity of what we design and how we design it is a really important point. So we're able to spread the impacts of our embodied energy over a much longer period of time. If we try to design our buildings with high quality, we'll want to keep them for a very long time, and they'll become part of our cultural heritage. Thank you. Questions?
Hi, Stuart. Thanks very much. That's very good. Where do you see new materials coming into this? Not that I know much about it, but something like graphene.
Yeah. Well, this talk would have had more graphene in it, but Farah very helpfully steered me into the realms of the built environment. So graphene. And there are others, right? So we're almost at the point where material scientists can create new materials, and possibly even at a point where we could choose materials for certain performances, which is why I think being able to take apart our facades and upgrade them when better materials become available is a really neat way to proceed. So for example, at the Warner stand at Lord's, we're using a tensotherm roof, so that uses aerogel, which is a fairly advanced material. If that could become commercially available, then that offers a potential solution to retrofit existing buildings for better thermal performance. Graphene, we're kind of exploring the potential uses of it at the moment, and it seems like it might have many applications in the manufacturing industry. So, for example, because it's so powerfully thin and easy to make, it could be used for packaging, so it could change our view on packaging and the recycling process to do with packaging. So there's going to be lots and lots of those contributions coming in, and I think the thing about the circular economy is it makes it kind of open for those things to come in, as and when, because we've got a plan to recycle and reuse our materials in the future.
Just pick up on one of the things you mentioned, which is really that perhaps our ownership model is what's driving the waste and the reuse, so that if the facade manufacturer owned the facade, then they would understand what was in it and they could recycle it and do something different in 20 years' time. Have you got any examples where that's actually happening?
Well, there are relatively few, but the Philips example is one. And at the moment, there seems to be a kind of exponential growth in the conversations around the circular economy at the moment. So I think there'll be a lot more examples in, say, 12 months' time. And there are lots of examples in the way that we're going about living our lives. People are moving away from ownership of products to a service. People want access to a service rather than ownership of a product. So I think there are lots of examples in our daily lives, but in the built environment, there are bigger hurdles, but it's coming.
Building in timber for London, considering pressure on land and small footprints and demand to build higher, are the timber constructions viable for this? What's the future for them?
So the project that I showed briefly, the life cycle tower, is a 20-storey building, and it mixes a concrete core with a timber frame around the perimeter. So the concrete deals with stability and the timber deals with the vertical load. And increasingly we're seeing more and more ambitious proposals in timber. So if you're designing the tallest building in the world in timber, probably by the time you finish there'll be another 5 or 6 or 7 around the world. So that benchmark's going up quite quickly. Although whether it's really appropriate for tall buildings is another matter. I think it's a really appropriate material for mid-rise buildings. I think we'll see a lot of that in London.
How do you think we could get all the engineers, the building services, structural, civils, to work together to really think about embodied energy in buildings as a whole, rather than different professions going off doing different things?
Well, again, I think if you had the circular economy in place, you could. We're all looking at the same information models now, so that provides a common platform. It's interesting, the more kind of multidisciplinary thinking we do, the better solutions we get. So just for example, I ended up in a microalloying conference. I don't quite know how, but I was the only structural engineer there. And so I was the only structural engineer there. I couldn't believe it. This is something that could change our industry quite dramatically. And this was a major conference about the topic, but it was full of people who understood the topic, but not the environment in which they were working. And I think that's one of the issues with our materials industry. It was quite a challenge for me to put together a talk that went from the beginning to the end, because it covers so many disciplines and specialisms. So just creating a more multi-dis environment would help. I'm not sure that answers your question, but responds to it.
I loved all the frightening statistics, and
Yeah, I'm sorry about that.
you didn't mention bricks. Now, bricks is a
Yeah.
huge architectural fetish,
Yeah.
and is a lumpen form of construction.
Yeah, with very low energy as well. And using lime mortars then allows you to recover bricks. And yes, that's a very sustainable part.
So not necessarily a bad thing going forward.
No, absolutely not. I think one of the talks I would like to do is a talk on more traditional building materials and how they fit into the picture. But as I started researching, this issue of carbon and carbon reduction is like we're not making any inroads into that at all. But building in timber and brick, it's a really good way to proceed. But it's also really difficult when you look at our cities and the kind of buildings we need in cities to imagine either brick or timber being a major part of the solution. And in fact, they're not the problem, but they're just not the solution.
Do you think that the political will is there? I mean, it seems like this is it is obviously a very urgent situation. Do you see that the sort of market model can provide the will to get it done in time?
I think so, because we have the Paris Agreement, which seems to be genuine, I think, with some fairly clear targets. So I think there's political will there. I think the circular economy is exciting because it kind of makes sense. It almost doesn't. You don't need to persuade people that it makes sense. If you've got a building that that you can treat as an asset with materials that are growing in value rather than just becoming obsolete and an obstruction to your site, that to me kind of makes a lot of sense. I guess one of the things we need to, the point I make at the end, of course, I'm passionate about architecture and design as well, and we kind of need to bring architecture and design into the process too.
You mentioned steel and concrete. You missed out glass, which is obviously use a lot of energy to produce. Every float line produce 700 tonnes every day. Do you think it's worth approaching the glass producers, the people who own the float line, to sell performance rather than facade makers? They might actually be the people who react to this circular economy.
Yeah, it could. Yeah, and I think, I'm certainly not a glass expert, but I think the recycling process seems to be in place as well if you can recover it. I think the example of the Empire State Building, which they've been refurbishing, they've taken all the glass away and recycled it. So that's certainly in place. And some of the facade systems we're looking at the the double glazed panels, the first thing that goes is the seal, and then you need to replace the facade. So if we could make systems that allow you to quite easily take that away and recycle it, then all of those things will feed into the mix. I'm not sure of how much carbon emissions the glass industry is responsible for.
Well, I think it's similar to steel in the way it's produced.
Yeah. Better get on with it then. Okay, we're good. Thank you. Thank you very much.
I think at the moment his talk is very relevant. I work in a lot of government sectors, and there's a big push for BIM, Revit, all the building information modelling, and everyone needs to work in that direction. I think that it's going too slowly, unfortunately. A lot of departments and people who are pushing for it don't actually have it as a client, and they don't realise the assets they currently hold. And it's just a legacy, really, and hopefully in a few years we'll be reaching the levels that he was actually saying we would reach.
It's my first time in Breakfast with Arab, and I have really enjoyed it. I think it is very refreshing that he started with kind of lots of data and kind of trying to make us understand what the situation is. And then it was really important that he also made us understand that there is a way forward, that is loads of people that is actually moving, not only to contain the situation, but to develop it so that we can all learn and kind of get somewhere. Going forwards, kind of people like me that coming here, we are learning what tools there are going to be out there so we can implement them in our own practice.
I thought Stuart's talk was really illuminating and inspiring because it takes an approach that really shows the width and the breadth of the problem around material efficiency, and how by comparing the efficiency of electrical and electronics with the built environment, it really forces us to look ahead at what the circular economy can bring in terms of reducing the impact, not just in energy efficiency of the buildings, but also in the way they're manufactured. So looking at the impact of steel and concrete and how different materials as well, different way of manufacturing some of the materials can be a significant change. It's really, really inspiring. And equally, from my perspective, I'm not in the architecture or construction industry, but I work in helping people to learn how to repair and reuse electrical and electronics. We'd love to inspire a different approach to the way such resources are used in the construction industry. So it was brilliant.